Okay, welcome everybody to the INQA seminar for Tuesday, the 11th of March, 2025. And it gives me great pleasure to introduce today's speaker, who is Puya Mirkarimi from the University of Durham. Puya will be talking to us about quantum optimization with linear Ising penalties in the area of customer data science. So Puya, over to you.
Thank you. Thank you for the invitation, first of all. And yeah, I will be talking about a linear Ising penalty method for encoding constraints in quantum optimization. And we'll be looking at an example problem from customer data science to demonstrate this. So in this project, we're looking at solving quadratic unconstrained binary optimization problems, QBOs. So this is any optimization problem where the objective function that you're trying to minimize is given in this form here. So you have a vector x of n binary input variables, and your objective function has linear terms with coefficients a and quadratic terms with coefficients b, which these coefficients are real numbers. So the task is to find the input x that minimizes f of x. And in quantum optimization algorithms, typically this will be done by mapping the problem to an equivalent Ising problem. So here you're going from binary 0, 1 variables to plus or minus 1 spin variables. And you can write it out as a Hamiltonian, where you have new linear coefficients hi, which are called local fields, and new quadratic coefficients j, which are called couplings. And the task then becomes to find the ground state of this Ising Hamiltonian. Various quantum optimization algorithms exist for finding the ground state of this Hamiltonian. So first, I'm going to introduce the specific problem that we'll be looking at as an example. And this example comes from a customer data science company called dunnhumby. So dunnhumby is a subsidiary of Tesco, and they work with a lot of different types of optimization problems. So for example, they might be interested in finding the optimal pricing of their products in a retailer, or maybe the optimal location of products on shelves to maximize sales. And in this talk, we are interested in finding optimal promotion plans for products. So to talk about this, I'm going to introduce this concept of promotion cannibalization. So to explain this, imagine you're a retailer like Tesco, and you decide to promote a certain product, for example, orange juice. After your promotion of orange juice, you might be interested in figuring out whether it was a good promotion and one that you would want to do again in the future. So you might look at the revenue from orange juice sales and find that during the period of the promotion, revenue for orange juice sales were elevated. And this makes it seem that the promotion was successful. However, you might look at revenue from other fruit juice sales and find that in the same duration of time that orange juice sales were elevated, other fruit juice sales, for example, pomegranate juice, might have fallen in their revenue, and maybe even the total amount of loss of revenue for these sales accounts for the increase in sales of orange juice. So this paints a different picture where you haven't actually generated new sales, and you've just shifted sales from one product to another. And this phenomenon is called promotion cannibalization. What we want to do is to find promotion plans that minimize the total amount of bilateral cannibalization between products that are promoted simultaneously. So to do this, what dunnhumby does is they measure product sales and use these measurements to build fine-grained predictive models. And these models are coarse-grained into this matrix C. So the matrix C has elements on the ith row and jth column, which represents the total amount of cannibalization on product I by product J when both products are promoted at the same time. So taking this matrix C, we can use it to build an optimization problem that we want to solve. So in the complete problem that we'll consider, we have 4 different fiscal quarters, and in each quarter we have some number of different products, and we might promote a given product on a given quarter. So if we have a variable that's spin up or in the state 0, then that represents a product that is not promoted on a given quarter. But if it's spin down or in the state 1, then you promote that product in that given quarter. So the objective function of the problem that we're trying to solve can be written like this. So we're taking a sum over all of the different combinations of products. So in this example, we have 6 products, and we're also taking a sum over the 4 different fiscal quarters, where we have a term that's quadratic and has the coefficient lambda t times Cij. So Cij comes from the cannibalization matrix C, and lambda t is a seasonal scale factor that represents the change in total sales between the quarters. So on a quantum annealer, for example, to actually implement the Ising Hamiltonian representing this problem, you would couple qubits together that are in the same quarter, and the strength of the coupling would correspond to the magnitude of the matrix element in the matrix C. So a larger value in the matrix corresponds to a thicker line on the diagram, which is a stronger coupling. So this is how we would encode the objective function, but in the real problem, we also have some number of constraints that we're interested in adding to the problem. So a real world scenario would have a lot of different types of constraints that the retailer would want to implement. And we will look at 3 different types of constraints. So in particular, we have a first set of constraints on the number of promotions per quarter. So this constraint says that on each of these columns, we want exactly C of these variables to equal 1. And then we have a similar set of constraints on the number of promotions per product, but in this case, we have an inequality. So for each row, as in for each product, we want between BL and BU promotions. So between BL and BU ones. And then finally, we have another set of inequality constraints that require that if you promote a product on a given quarter, you don't also promote it in the next quarter. So we don't have any consecutive promotions. So the objective function we mentioned could be encoded easily in an Ising Hamiltonian, but those constraints that we just mentioned aren't in the form of a cubo. So they're something that are separate to the objective function. And so we need to think about how to implement them in our quantum optimization algorithm. So various methods exist for doing this. The most common method is the penalty method. And in the context of quantum optimization, typically a quadratic penalty function is used with the aim of structuring the penalty function such that when you add it to the objective function, you raise the value of the objective value for all of the states that don't satisfy a constraint, while keeping the objective value the same for states that do satisfy a constraint. And then your new objective function would have a feasible ground state. So we will be looking at an alternative penalty method with only linear Ising terms, and this is very similar to previous work by Ohzeki that essentially results in a very similar method coming from a different angle. And there are a variety of other approaches that could be used, which I won't go into in this talk. So to explain the quadratic penalty method, we are going to use this diagram here. So in this diagram, we're representing some cubo problem. which isn't the promotion cannibalization problem that we're using as an example. But for this cubo problem, we're plotting the objective value as a function of the Hamming weight of the solution. So the Hamming weight is the number of ones in the solution. And for each Hamming weight, we're plotting the solution with the lowest objective value in a darker color and connecting these points with a solid line, just to guide the eye. So in this case, for this cubo, we have a solution with the minimum objective value at a Hamming weight of 4. But let's say we want to add a constraint that requires the solution to have a Hamming weight of 2. And the way you do this with a quadratic penalty is you take your original objective function and add this penalty function, which is centered around a Hamming weight of 2. So this penalizes all states that do not have Hamming weight of 2, and you can rescale this function with the penalty strength parameter alpha 2. And for a large enough value of alpha 2, you get a new objective function that has the minimum objective value shifted from a Hamming weight of 4 to a Hamming weight of 2, and that solution is the optimal solution of your constraint problem. So this works quite well in implementing a variety of different constraints, and you get the correct ground state in your Hamiltonian. But when you actually apply it in the context of quantum optimization, it does have its disadvantages. So firstly, if you expand out the brackets in this quadratic penalty, you get quadratic terms with non-zero coefficients between all pairs of variables in the constraint. So physically, if you were to actually want to implement this Hamiltonian on a device, that means you would need to physically couple the qubits representing those variables. So you would need all-to-all couplings between those qubits to do this. And many types of quantum computers today don't support the required couplings to actually do this. So you need to use some approach to account for this. And secondly, another disadvantage is that if alpha 2 is large, or the absolute difference between k and m over 2 is large, then this quadratic penalty would introduce large local fields or large couplings to your Ising Hamiltonian. And given that your physical device has a maximum physical energy scale over which you can implement these interactions, then you are effectively reducing the effective dynamic range of your qubit interactions if you add this penalty term to the objective function, which can hinder performance. So we can look at other approaches that might not have these disadvantages to the same extent. So one approach would be to use a linear penalty, and this has been done before in classical optimization. So in quadratic programming solvers, people have used this form of linear penalty where you're essentially replacing the squaring of this term in the brackets with an absolute value operator, and you get the correct shape of a penalty function. So you're still not contributing anything to the Hamming weight of 2, but you are contributing a positive value to all of the Hamming weights. But this absolute value operator is a non-Ising operation, so you wouldn't be able to directly represent it as an Ising Hamiltonian. So this presents its own difficulties. It has been done before in the form of a generalization of QAOA. So quantum approximate optimization algorithm, you can build a circuit that essentially performs that absolute value. However, this comes with the cost of a larger circuit depth and will have its own overheads. So this is an approach that you can take, which is easier in the QAOA. But we will be looking at a different approach where you're not taking the absolute value, you're just having a linear function. So this looks like this, where your gradient is your linear penalty strength for alpha 1. And now your penalty function doesn't necessarily have, or doesn't have a minimum at some Hamming weight in the middle where you want. It always has a minimum at the largest Hamming weight if alpha 1 is negative. Because of this, this penalty method doesn't apply to all problems, so it can't constrain every possible problem that you'd want to look at. It only works in certain scenarios. And we found that in the problem that we're considering, it works quite often because of the structure of the problem. So the structure that results in the nice property is the fact that the objective function of the problem that we're considering has only quadratic terms with non-negative coefficients. So the cannibalization matrix element C can either be 0 or some positive value, can't be negative. And in this case, we're looking at a simplified form of the problem with a single fiscal quarter to just make the graph easier to visualize. But if you plot the same graph as before, you find that the minimum objective value as a function of Hamming weight is monotonically increasing because of the non-negativity of the matrix elements. So what this essentially means is that quite often adding a linear Ising penalty in this form is enough to produce a new objective function with the correct Hamming weight in its ground state. So here, if you tune alpha 1, then you can shift the minimum objective value from a Hamming weight of 0 or 1 to a Hamming weight of 2. And a point to make here is that the tuning of alpha 1 is now more difficult than the tuning of alpha 2 for the quadratic penalty method. So if you are going to use the linearizing penalty method, there's an extra overhead in terms of classically tuning this parameter that will be there, which isn't quite as severe when you're using the quadratic penalty method. But to compare the two penalty methods, if you look at the quadratic penalty, you end up multiple couplings between the variables as well as using local fields, whereas with the linear penalty, you only need local fields to implement the constraint because it's all linear. And as we alluded to previously, this has its benefits when you're actually implementing this on a device. So in the context of quantum annealing, on the left, we have the logical graph of some problem that we want to solve. And here the nodes represent variables and the edges represent quadratic terms and non-zero quadratic terms between two variables. And we want to map this onto the graph representing the physical device of the quantum annealer. So if, for example, our qubits are coupled in this way shown here, so here we have a square lattice where the nodes represent physical qubits and the edges represent physical couplings, then if we look at, for example, variable number 4, it has couplings with 5 other variables, whereas our physical device has a maximum of 4 couplings per physical qubit. So there's no way you'd be able to directly map this graph onto the graph on the right. So you wouldn't be able to directly represent the Ising Hamiltonian. And in quantum annealing, a method that's used to get around this issue is called minor embedding, where you represent each variable with a chain of ferromagnetically coupled qubits. So the aim here is to have a strong enough coupling between the qubits in your chain that they all have the same value and they essentially represent the same variable. And then as you make the chain longer, your variable has coupling, more and more couplings to other variables. And so you can find some graph that represents your original graph with the added overhead of requiring more physical qubits than there are logical variables in your problem. Another, as well as requiring more qubits than variables, another issue is that as your chains become longer and the strength of the couplings between the qubits and the chains become stronger, you end up having a negative effect on the effect dynamic range of your qubit interactions because of the chains themselves as well. So to look at the problem, the example problem that we introduced to do with promotion cannibalization, and just to note, these results are more general than just the promotion cannibalization problem. We're just looking at this as an example, but really the objective function for a lot of different types of problems would be very similar. So on the left, we have the graph for the logical problem if we're using a linear penalty to encode the constraint, and on the right, we have the graph if we're using a quadratic penalty. And when we're using a linear penalty, the only couplings we need between the variables are the ones that come from the cannibalization matrix. So we end up having a relatively sparse graph because the matrix C is relatively sparse. In comparison on the right, in this example, we only have one fiscal quarter. So we have one constraint acting on every variable, which is essentially a k-hot constraint. And what this ends up doing with a quadratic penalty is coupling every qubit to every other qubit, so every variable to every other variable. So when it comes to solving this problem on a quantum annealer, we ran experiments on a D-wave advantage QPU, and this is the hardware graph of that device when the nodes are qubits and the edges are physical couplers. So if we take the problem that's constrained with a quadratic penalty and minor embed it on the device, we get the graph shown on the right. So here we've got 100 variables in the original problem, but we end up needing around 1,300 physical qubits after minor embedding. So that's quite a large overhead, but if we use a linearizing penalty for the same problem, to represent the 100 variables, we only need around 150 physical qubits. So we still need to represent our variables with chains, but the length of these chains is a lot shorter, so much fewer qubits are needed. And here we're showing the results from actually running those problems on the device. So this is again for the problem with one fiscal quarter and 100 products, and the constraint is to choose 50 products to promote. So for a number of different instances of the problem, we've sampled the annealer many times, and on the left, we're plotting the fraction of those samples which represent solutions that satisfy the constraints. So these are the fraction of feasible samples. And in blue, we're using the linear penalty method, and in orange, we're using the quadratic penalty method. So we can see that even though the quadratic penalty method uses more physical resources to implement the constraints because it uses couplings, it doesn't perform as well on average in actually implementing the constraint compared to the linear penalty method. And this is probably because of the overhead in terms of minor embedding that we talked about, which is ruining the dynamics on the annealer. So on the right, we're plotting the histogram for the approximation ratio, or the best approximation ratio of the sample set for each problem instance. So the approximation ratio is 1 if you've sampled the optimal solution, and it's 0 if you've sampled the worst possible solution. With the quadratic penalty method, we get approximation ratios of roughly between 0.5 and 0.7, which indicates that the solutions are only slightly better than what you would have if you were randomly guessing solutions, and definitely not close to optimal. Whereas when you're using the linear Ising penalty method, you sample the optimal solution in most cases, and even if you don't get the optimal solution, you get very close to it. So we also ran experiments on the full problem with 4 quarters, and this time with 10 products. And when in cases where the linear penalty method is successful in producing the correct constrained ground state, you get similar results as in the previous slide. So a big advantage of using the linear penalties. But in many cases, actually, you can't apply the linear penalty method to all of the constraints that you want. So for this problem, we're considering applying linear penalties only to the constraints on the number of promotions per quarter. So these are the vertical constraints that we showed earlier, 4 of these. And if we look at the instances where we cannot tune the 4 alpha-1 parameters such that all 4 of these constraints are satisfied, then we can use an alternative approach where you use a combination of quadratic and linear penalties. So this is what we're plotting here. So in the top panel, we have instances where we've applied linear penalties to the first and 4th quarters and quadratic penalties to the 2nd and 3rd. And in the bottom panel, we've applied linear penalties to the 2nd and 3rd quarters. So what we're actually plotting in these histograms is the difference in the objective value between using the linear penalty method for 2 of the quarters and using the quadratic penalty method for all 4 quarters. So a negative difference in f of x indicates that actually using linear penalties has some benefit, whereas a positive difference shown in red indicates that using all quadratic penalties is actually the better approach for that instance. And in these examples, the number of instances where the linear penalty helped and where it didn't help are very similar. So in the top case, there are more instances where using a linear penalty actually helped, and in the bottom case, there are fewer instances where it helped. And we've also determined that these results are statistically significant, so the difference isn't due to just random chance. And the reason why we think the linear penalty method was more useful in the case where we've applied it to Q1 and Q4 is because in our formulation of the problem, the term lambda t, so the seasonal scale factor, which scales everything up, is largest for Q1 and Q4, which means the underlying couplings in the unconstrained problem are stronger for Q1 and Q4. So if you were to maximize the benefit in terms of the effective dynamic range of using the linear penalty methods, you would want to apply it to Q1 and Q4. So I think our thought is that maybe the reason why we're getting better performance in this case here is because we're maximizing the benefits of the dynamic range when using the linear penalty method. So this is potentially some evidence that not only does the minor embedding matter when it comes to choosing which penalties to make linear, but also the dynamic range effects matter. And as well as running experiments on quantum annealers, we've also simulated quantum annealing in the case where we have a closed system and all of our qubits are all-to-all connected. And on the left, we're plotting the success probability, so the probability of finding the ground state of the constrained Hamiltonian, and on the right, we're plotting the feasible probability, so the probability of measuring at the end of the anneal and finding a feasible state. So looking at the graph on the left, we find that across the range of NP, which is the number of products, we find an advantage of using the linear penalty method in these problems. And on the graph on the right, a thing to note would be that the distributions, which represent different values of the y-axis for different instances of the problem, so the distributions are wider when using the linear penalty method, and we think that this is because of the difficulty of tuning the alpha-1 parameter and the fact that the linear penalty method is more suitable for certain instances than others. So overall, it's quite nice to see that even in the scenario where we don't have the minor embedding issue to consider, we still have signs of a performance enhancement when using linear penalties in simulations. And finally, we also simulated the quantum approximate optimization algorithm using linear and quadratic penalties with the same problem instances. And one thing to mention that I forgot is that this gray dashed line is the success probability that you would get from randomly guessing a solution. So the difference in performance here isn't as dramatic, but you still see an increase in performance when using linear penalty methods. And this is interesting because in the QAOA, you don't have quite the same a direct representation of a dynamic range, as in what I mean by this is you can rotate your qubits by any arbitrary angle. So the concept of dynamic range is a bit more subtle in the QAOA, but these results still indicate that they make a difference, and the linear penalty method is able to be more efficient in this respect and lead to better performance. So to summarize, we've found that the linear Ising penalty method can successfully encode constraints in many of the problems that we've considered for the promotion cannibalization problem. And it only uses linear terms, which has benefits in terms of the minor embedding and dynamic range efficiencies. And this led to better performance on a D-wave annealer. And we also found that combining the linear and quadratic penalty methods work for problems where only the linear penalty method on its own isn't suitable. And finally, positive result in simulations of quantum annealing and the QAOA in the setting of a closed system with fully connected qubits. So if you'd like to learn more about the results that I haven't presented in this presentation, I would point you to these two papers. So thank you for listening. I'm open to any questions.
Great, thank you very much, Puya. Very interesting presentation. Thank you. And as Puya says, I'll open this up for questions if there is anybody who has questions for Puya. Well, perhaps I'll kick things off then, use the chairman's prerogative. I'm interested in comparisons between QAOA and quantum annealing within your closed system simulation. You've done that. Yes, my first question is, whether it's meaningful to start to think about comparisons between this that I see now and the quantum annealing result. Maybe the second question is whether you've tried QAOA on some real hardware, because you have tried that with the annealing clearly, but you haven't tried it with the QAOA, or at least you didn't present that.
Yeah. So to make a fair comparison between the QAOA and quantum annealing, I guess you'd have to match the number of layers to correspond to the duration of your anneal. So you'd have to come up with an equivalent number of layers to make that a fair comparison, which is not what we've done. So we just picked some number of layers. I can't remember what it was in this case. It was more than one. I can't remember what it was. And Yeah, so that number was picked just based on the restrictions in terms of compute power that we had. So we just tried to go as high as possible while still being able to simulate it. So yeah, that would mean you can't directly compare this graph to that graph and say that QAOA is done worse because the success probability is lower, because we haven't. It might just be that that's because we're using a longer duration here. So yeah, that would be something. And also, we haven't in this study looked at optimizing everything that you could possibly do in terms of the classical optimization steps. So yeah, I wouldn't say we could make many conclusions based on this, other than just pointing out that in this case, quantum annealing with the results that we have did perform better, but it could be that if you were to do the QAOA a bit more intelligently, you might be able to find better results. And we also haven't tried running the QAOA on a real device. No.
Just while we've got this plot in front of us, what is plotted on the right hand side? That's so PS on the left hand side is the probability of success. What is PF on the right hand side?
So PF is the probability of finding a feasible state. So you produce some state, and then this is the probability of it satisfying your constraint. Yeah.
So the success probability on the left is the optimal solution. Have I got that correct? So
exactly. Yeah. Yeah.
How do you know your optimal solution a priori? Have you run this through Garobi or something?
Yeah. In this case, we've run it through Garobi, but I think you could also just they're small enough that you could solve them.
Yeah. Good. And any other questions from anyone in the audience? Perhaps I'll allow myself just one more in that case. So you said quite early on in your presentation that this linearized penalty works well for certain types of problems, and in particular, it worked well for your problems where the quadratic coefficients were all the same sign.
Mm-hmm.
And as a result of that, your energy as a function of Hamming weight was monotonically increasing.
Mm-hmm.
Yeah, maybe you could find that graph. Yeah, this graph. So this monotonically increasing energy with Hamming weight is a feature of when you restrict your coefficient C to be positive. Fine, but doesn't this therefore mean the problems are easy in some sense? Because I mean, I know the converse is true, and to me, Malbash has done lots of this sort of stuff where you have some horrid functional dependence of the energy on the Hamming weight with a big dip or something at high Hamming weight, and those are going to be hard problems. So is that a fair criticism of what I'm seeing here, or am I being unnecessarily negative?
So I guess to point to another problem that would have only positive values in its objective function would be the traveling salesperson problem. So you would never have a negative distance between two cities. So I think, yes, if all you were doing was minimizing this with no constraints, then that would be an easy problem. But I think the combination of a objective function with non-negative terms and constraints can make the problem hard.
Okay.
And I'm not claiming that we've proved this problem in particular is hard. We're just motivating it by the fact that it's solved in the real world, and it's an actual problem people try to solve. I'm not aware of the work, but I think you said to me, Malbash. Yeah, I'm not aware of that work. But yeah,
I can point you in the direction of that, I think.
Yeah,
you can dig it out. But yeah, and if all your weights are the same time negative, is that as easy as just changing the slope of your linear constraint, or is it more complicated than that?
If it's negative. Yeah, I used to. So then even if you had 0 Hamming weight, then it would still be there. And as you increased Hamming weight, it would go down. I would have to think about it, but
Okay.
yeah, it feels like it should still be able to work.
Maybe.
But I'd have to think about that to make sure.
And the equivalent problem would be well, things that correlate rather than things that anti-correlate or something like that.
Yeah.
Okay. Cool.
Which is definitely an interesting problem to think about. Yeah.
I shall leave that with you. Right.
Yeah.
Good. Let's round it up there and thank Claire once more for a very nice presentation. A round of applause from me on behalf of everyone attending, and we'll conclude there. Look forward to seeing everyone next week at the next INQA seminar. Thanks, Claire, once again. Cheers.
Thank you.
Bye-bye.
Bye-bye.